Hi there, Mr. Sutton here, bringing you the AB Calculus 2-6 Part 2 homework solutions on continuity. On this problem, we're being asked if this piecewise function is continuous at x equals 2, a border value. So we're going to have to check out the left, right side limit and also the function value at 2, all three of those things possibly. So let's start by checking out the left side limit as x approaches 2. That's going to be using this rule as we're coming from the left here, this top rule. So 2 squared gives me 4 for that left side limit. For the right side limit, we're going to use this other rule down here. So here's our right side limit. That's going to be 3 times 2 plus 1, which is 7. Now we could find the function value as well. It's also going to be 7 because this is 2 less than or equal to x. However, we notice immediately that these limits don't match up. Since those don't match up, our limit does not exist, which means that we're not going to be continuous at x equals 2 for this function. On this problem, we want to know if this piecewise function is continuous at x equals 0. So let's do left, right, center here. The left side limit, as x approaches 0 from the left, that's going to be plugging 0 into this first rule right here. 3 times 0 gives us a limit of 0. Now for the right side limit at 0, we're going to be plugging 0 into this rule where x is just a little bit more than 0. So we have 0 minus 2, which is negative 2. All of these x terms get zeroed out, so we just have 6 downstairs. So that's negative 1/3 if we reduce that. And let's go ahead and find the function value. Although we probably don't really need to, but let's do it anyway. So f of 0 is going to be 3 times 0, which is 0. Okay, now the big issue here is that these limits don't match up. Because they don't match up, that means the limit as x approaches 0 of f of x, in general, the two-sided limit, does not exist. Because the limit does not exist, that breaks our condition of continuity, so we know that we are not continuous at x equals 0 for this function. On this problem, we're trying to find an a value that makes this piecewise function continuous. So to do this, we're going to take a look at the left and the right and the function value at negative 2. So the left side limit as x approaches negative 2 from the left, we're actually using this bottom rule here. This is the rule for x less than negative 2. They kind of wrote things out of order, but there's no rule against that. So we've got 5 times negative 2 squared minus a for the left side limit here. And then that's going to be, let's see, 5 times 4 is 20, so 20 minus a. We don't know what a is yet, so we're not going to go any further with that. Let's find the right side limit now, which happens to be the same as f of negative 2. It's this rule up here. So for the right side limit and f of negative 2, both of those, we're going to do square root of 7 plus 2. So square root of 9, which is 3. And now we're just going to let 20 minus a and 3 equal each other because the left, right, and the function value have to all match up. So if 3 and 20 minus a equal each other, if we, let's see, subtract 20 from both sides and divide by negative 1, that's going to be an a value of 17, right? Because you have negative 17 divided by negative 1. There you go. For this problem, we're trying to find the a and b values that make this piecewise function continuous. So to get the a value, we're going to start by finding the left and right limits at the border value 2, and also the function value there. So the left side limit, it's actually going to use this first rule, x less than 2. So we're going to do square root of 3 times 2 minus a. So this is the square root of radical, or this is radical 6 minus a, and we can't really go any further because we don't know a yet. And now we're going to take the right side limit at 2, which also happens to be f of 2 because we have this equals here. Either way, that is going to be 1/2 times 2 squared. Half of 4 is 2. And now we have two expressions that we can set equally to each other that have to be equal for this function to be continuous. So we can say radical 6 minus a equals 2. Squaring both sides, we have 6 minus a equals 4. And then that means a must be 2. And just to be on the safe side, let's actually go back to the original equation and plug in 2 to make sure it works, because sometimes you solve these radical equations and you get extraneous roots. So we've got the square root of 6 minus 2, which is the square root of 4, which is 2. All right, we're good to go. Next one, solving for the b value. Now we're going to do left, right, and center at x equals 6. So the left side limit at 6, which also happens to be f of 6, that's going to be 1/2 times 6 squared. Half of 36 is 18. And now the right side limit at 6, we're using this last rule for the x values greater than 6. That's going to be 5 times 6 plus b. So 30 plus b. So we know then that 18 and 30 plus b are equal. Subtracting 30 from both sides, we get b equals negative 12. For this problem, we're given this g function, and we're asked which of the following reasons would be the reason that our function is not continuous at this border value of x equals 3. So we've got g of 3 undefined, limit doesn't exist, limit does not equal function value. So let's go through and actually find all three things. So the left side limit of g, that's going to be using this top function here with x less than 3. That's going to be sine of 3 pi over 4. So just a little quick unit circle trig here. This would be sine of essentially 135, which is the quadrant 2 version of 45 degrees. So that's going to be root 2 over 2 if you do your unit circle math. And then right side limit as we approach 3, that would be using this bottom rule down here. So that's going to be 3 radical 2 over, let's see, 12 minus 6 is 6. 3 root 2 over 6 is really just radical 2 over 2, which matches what we got for our left side limit. And then finally, g of 3 itself, the function value when x equals exactly 3, is just going to be 3 radical 2. So let's look at all these now. We see here that g of 3 has this value of 3 radical 2. Well, it has a value. It exists. It's not undefined. So option 1 is no good. And then we see here these limits match up. So the two-sided limit of g of x is also radical 2 over 2, which is to say it exists. So option number 2 then is also incorrect. Well, that leaves only option number 3, and we see here that yes, radical 2 over 2 and 3 radical 2 are not the same thing. So that means that option 3 is the only good answer, meaning answer choice A is what we need. For this problem, we're given this crazy piecewise function over here, and we want to know at what values of x is f of x continuous. So that's a pretty broad question with a piecewise function, but notice that the only answer choices I have involve these border values at 0, 1, and 2. So we're just testing continuity at the border values. All right, for that we're going to need left and right side limits and function values at each of these. So let's start with 0. Left side limit at 0, that's going to be sine of 0, which is 0. Right side limit there, we're going to be using this second function where we have x greater than 0. So that's going to be 0 squared, which is also 0. And then the function value is just the same as the right side limit because we have the equals there next to the 0. So that's also 0 for f of 0. Since the limit at 0 and f of 0 match up, that proves that we are continuous at x equals 0. Now let's move on to the x value 1. Left side limit at 1, we're using this second rule here, so 1 squared is 1. Right side limit, we're using the third rule, 2 minus 1 is 1. For f of 1, that matches the right side limit because we have the equals next to the 1, so that is still 1. Since the limit at 1 and f of 1 match up, we say that our function is continuous at x equals 1. Okay, one more to go. So now we're basically picking between answer choices D and E. So at x equals 2, left side limit, that's going to use the third rule where x is less than 2. So 2 minus 2 is going to be 0. And now right side limit, that uses our fourth and final rule. 2 minus 3 is negative 1. The limits don't match, so our limit does not exist. That breaks one of our rules of continuity, so we can say that our function is not continuous at x equals 2. So then only 0 and 1 have continuity out of these choices, so that would be choice D. On this problem, we're given a piecewise function here with a magical mystery k value in there. If f is continuous at 3, which just so happens to be the border value, what's the value of k? So we have to basically do left, right, center on this one. We have to find the left and right side limits at the border value 3 and also the function value and make sure that those all equal each other, and that will reveal the k value for us. Because we're guaranteed this is continuous, so we know all of that stuff is going to match up. So let's go through it. Left side limit at 3 also happens to be f of 3 because we have the equals here. So that's going to be 3 squared plus 2 using that first rule. So that comes out to 11. The right side limit, we're going to use this second rule where x is greater than 3. So that's 6 times 3 plus k, which is 18 plus k. And because we're guaranteed this is continuous, that means 11 and 18 plus k must equal each other. Subtracting 18, we get k equals -7. That's choice A. For this problem, we're given this piecewise function, and we want to know what is true about this function. So let's go down the line. Option 1, limit of f of x exists as x approaches 3. Well, let's find the left and right side limit. The left side limit at x equals 3 here, we're going to use the earlier function, the less than 3 function. So that's going to be 3 plugged in here, 3 plus 2, which gives us 5. And now we need the right side limit. So that's going to be 3 plugged into this other rule. 4 times 3 is 12, minus 7 is also 5. So the limit overall, as x approaches 3, is 5, which is to say it exists. So that means that this option here is legitimate. So let's move on then. So we can eliminate anything that doesn't have 1 in it, like D and E. All right, so option 2, f is continuous at x equals 3. Well, for continuity, we need the function value to also exist, so let's check into that. We see here that f of 3, if we plug 3 into the function, there's actually no rule for what happens when x equals exactly 3. We have less than, we have greater than, we don't have exactly 3. So that means that f of 3 is actually undefined, does not exist. So option 2 is a no. Because we're not continuous at 3, option 2 cannot be accepted. All right, so option 3 then, limit as x approaches 1 equals 3. Well, 1 is not a border value. It's actually firmly inside this first rule. So this limit is really just taking the limit of x plus 2 as x approaches 3. So that means that we're just doing 1 plus 2, which is just going to be 3. And that turns out to be true. So we want options 1 and 3, which is choice C. On this problem, we're given this function of x minus 2 over 2 times absolute value of x minus 2. Now, we have seen this function type before. We want to know which of these things is going on here. In order to analyze any of these, we need to figure out the limit as x approaches 2, because that's what all these answer choices are talking about. In order to do that, we need to write this as a piecewise function. So I'm going to let all this stuff equal f of x just so I can quickly refer to it without writing all of this over and over again. And I'm going to set up a piecewise function for this. My border value is going to be x equals 2 because that's what makes the stuff inside absolute value 0. So that separates the x values that make absolute value insides negative versus the x values that make the stuff inside positive. So I've got a rule for x less than 2 and a rule for x greater than 2. I can't have a rule for x exactly 2 because that would give us 0 in the denominator and the numerator for what it's worth. All right, so our first rule then, for when the stuff inside here comes out negative, we have to force it to be positive. So to simulate what absolute value does, we'll just negate all of the stuff inside absolute value. So I'm going to rewrite this as x minus 2 over negative 2 parentheses x minus 2. This negative out in front here basically forces the stuff inside here to come out positive after it becomes negative. For my other rule now, x greater than 2, well, when you plug in x values bigger than 2, that makes all the stuff inside here positive. So in that case, absolute value really doesn't have anything worthwhile to do, and we're just going to replace it with a parentheses. So this will be x minus 2 over 2 parentheses x minus 2, no negative out in front. So this simulates absolute value. Now, to take the limits, we actually have to cancel out these x minus 2's. So that'll give us negative 1/2 for the top rule and positive 1/2 for that bottom rule. All right, now let's take our left and right limits so we can see if we have any discontinuities. Left side limit as x approaches 2 from the left is going to just be this -1 constant value right here. And as we approach 2 from the right side, that's giving us this second rule's constant value of 1/2. Since these are two constants that don't equal each other, that means that we have a jump at x equals 2, which would be option C. On this problem, we're given this g function, and we're told it's not continuous at 2, and we want to know why it isn't continuous. So we have g of 2 not defined, limit does not exist, limit does not equal g of 2, and some combination of these reasons. Well, let's check out our limit here. So left side limit of the g function at 2, that's going to be actually using this bottom rule here. They wrote them out of order for some reason, but you always have to be reading your intervals. So we've got 3 times 2, which is 6, minus 7 gives us -1 for that. And now let's check out the right side limit, for which we're going to actually need the top rule, because this is the x greater than 2 rule, so we're coming from the right if we use this rule. That's going to be 2 minus 3, which is also -1. So then our two-sided limit is -1, which is to say it exists. So the option B, that it does not exist, has to be rejected. And we could also reject D because that has answer B in it. But let's keep going here because there's a few more to choose from. So let's check out g of 2 now. G of 2 is exactly -5 because that's what you do when x equals 2. Well, g of 2 exists. If it's -5, it exists. So that means we can rule out answer choice A. Well, that leaves only answer choice C because D had B in it, E had A and B, which was bad news, so C by process of elimination. But just going a little further here, we notice that the limit as x approaches 2 of g of x, -1, and the value at x equals 2 of g of x, -5, they don't match up. So this is actually true, choice C.